Today she'll be talking about integer valued polynomials with prescribed set of lengths. Okay, this is her work together with Sophie Ritchie and Roswitha Risner. And yeah, she is from Kabale University, and I hope you will enjoy her talk. And let's listen keenly, and hopefully if you have any questions at the end of it, please prepare a lump sum. She is a teacher, so she loves questions. Prepare them as many as you want. Yeah, and then, okay, so we can start. Dr. Sarah Nakato, please take over.
Thank you, Nazrin. Thank you for the introduction. Yes, I'm a teacher and I like teaching. Yes, good evening, everyone. Good afternoon. Thank you once again for joining our seminar. Today, I would like to share with you integer valid polynomials with prescribed sets of lengths. And this is joint work with Professor Sophie Frisch and Dr. Risner. So I'll start with some preliminaries on integer valued polynomials and factorizations. Then I'll go straight away to sets of lengths in int D. So our integer valued polynomials can be defined on arbitrary domains. In particular, if we have a domain D with quotient field K, what we call the ring of integer valued polynomials on D, which we denote by int D, consists of polynomials with coefficients from K that map D to D. When inputs and elements of D, the output should be in D. So that is int D. It's a subring of Kx in particular. So there are special elements with coefficients from K such that when you input an element of D, the output is also in D. So what we know for sure is that you can always write a polynomial with coefficients from K as a quotient G over B, where now G is in Dx and B is a non-zero element of D. So this is possible. And if a polynomial of Kx is written in that form, it's in int D if and only if B divides the images GA for all A in D. So this follows from the definition. Okay, so a quick example, the general one, is any polynomial with coefficients from D is always integer valued, because in that case, the denominator is either 1 or -1. We have nothing in the denominator in particular, more or less. So we are not worried about what is dividing what. So Dx is trivially in int D. Then other examples are on a case-by-case basis. In other words, D varies over rings, other rings. It's an arbitrary domain. For example, when we have int Z, we also have examples in that case and also for any arbitrary ring. But then int Z is very special. That's why I'm highlighting it. And whenever we say integer valued polynomials without mentioning the domain, we are referring to integer valued polynomials on Z, because it was the first one to study it. So the ring of integer valued polynomials is the ring int Z. Now these are polynomials with rational coefficients, still such that when you input an integer, the output is an integer. So that is int Z. And in particular, it's also a subring of Qx. So there are elements with rational coefficients, but with this special property, that when you evaluate them at an integer, what you get must be an integer. So int Z is very special. More generally, for an arbitrary domain, you have to check on all elements, but for int Z, you don't have to check on all integers. It is known that a polynomial f in Qx is in int Z if and only if f of A is in Z, for all A ranging from 0 to the degree of that polynomial. So for this case of int Z, you don't have to worry about checking on all integers. You only have this test set, 0 up to the degree of that polynomial. Once the images are integers, you conclude that that polynomial is integer valued, or it's in int Z. A quick example. This polynomial is integer valued because when you pick Is it integer valued? We have to check anyways. Is this integer valued? You have to check the degree is 2. So we check images 0 up to 2. F of 0 is what? Is a half. So already my assumption was wrong. It's not integer value because f of 0 is a half. It's not an integer. So we conclude that this is actually not integer value. Why? Because f of 0 is a half. We don't even have to check on other elements. Whereas this particular one, so for this is integer valued because f of 0, when you substitute, you get a 1. F of 1 is a 2. F of 2 is a 4. So this is integer valued. Yeah, so that's how we really check the integer valued polynomials. So if we have an arbitrary domain D, that's another case. We don't have such a test set, but then there are still other domains where we have similar test sets, though they are not so neat as in the case of int C. Great. So we also have more examples. We know that a product of n consecutive integers is divisible by n factorial. What does that mean? If I pick such a polynomial, when I put in an integer, I'll get n consecutive integers, or in this case, there are 4 consecutive integers. They have to be divisible by 4 factorial, which is 24. What does that mean? This is already integer valued. So one can pick really any as long as one is getting consecutive integers, your integer valued over anything. If there were 3, would have 3 factorial. If there were 2, would have over 2 factorial. All right, so each binomial polynomial, still stemming from this result, each binomial polynomial is integer valued. Each binomial polynomial is in int C. Because still you're going to get n consecutive integers. They have to be divisible by n factorial. Great, so that is int C, it's friendly. So actually these binomial polynomials are very special in int C because these form a Z basis of int C. In particular, every integer valued polynomial can be written as a Z linear combination of binomial polynomials. And the converse is also true. When I get binomial polynomials and as the linear combination of those binomial polynomials, I get an integer valued polynomial. So actually in Sage Math, the professor who implemented these integer valued polynomials in Sage Math used this basis. And more generally, because we can have an extension again of the same basis, and he has 2 bases in that case for integer value polynomials. So one can check it out under Sage Math. Okay, so this structure of integer valued polynomials is friendly to work with. Like we said, it's just a subring of kx. For int Z, it's just a subring of qx. They are usual elements we work with in under polynomials. I mean, the coefficients are just rational numbers. So it's friendly to work with, and it's a source of examples and counterexamples. For example, int C is non-Noetherian. Not all the ideals are finally generated, and actually one can construct an ascending chain that never terminates. And that ascending chain is actually the ascending chain for the binomial polynomials. Yeah. And more generally, there's other domains where int C is non-Noetherian. For example, when D is Noetherian and one-dimensional, still, in the non-trivial case, int D is non-Noetherian. But now, for my case, and for this particular talk, we are focusing on the fact that int D, in general, is not a unique factorization domain. So we have non-uniqueness of factorizations into elements. So a quick one in int C is this polynomial. As innocent as it is, yes, we expect it to factor as x times x plus 1. But it also has another factorization. Why? Because this is integer valued. One can say these are 2 consecutive integers. They have to be divisible by 2 factorial for any integer we pick. So this is integer valued. Another person can say, this covers the even numbers. When you put in an even number, this will be even, in other words, divisible by 2. If you put in an odd number, this will be divisible. This will be even, in particular, divisible by 2. So this is another factorization of this particular element. All right, so more can happen. For example, in this case, we have this polynomial. Still, it can factor into these 2 irreducibles, and in those 2 irreducibles. Likewise, because this part itself is integer valued for the same reason of it being a product of 2 consecutive integers. The same applies to this. Or still the same reason, evens and odds. Yeah. So these 2 are factorizations of this particular element. But then let's look at maybe the definitions now of factorizations and so on. So our factorization terms, I guess now they are very familiar to us. So R is a commutative ring with identity. A non-zero element U in R is called a unit if there exists a B in R such that UB is 1. In particular, the units are the invertible elements. These are the invertible elements in particular. For example, the units of Z, as we know, the 1 and -1. And actually, the units of int Z are exactly the units of Z. So even int Z has 1 and -1 as the units. And more generally, int D and D share units. Great, so another definition still, it's very familiar to us now. A non-zero non-unit R in R is said to be irreducible if whenever R is the product AB, then either A or B is a unit. So you can't write R as a product of 2 non-units. So those are the irreducibles. In other words, we can't split them. Whatever we split, the parts we get are not in that particular ring. For example, our usual prime numbers, as we know, they are always irreducible. They are irreducible in Z, and more generally, the prime elements are always irreducible in that particular ring under consideration. And then by a factorization, still, we are referring to an expression of R as a product of irreducibles. Still, that's what we call a factorization. And the length, so like I said, most of us now know these terms, but we need them for this talk. The length of the factorization is the number of irreducible factors. Number of irreducible factors is what we call the length. And then we say that indeed R and S are associated, denoted by that, if they differ by a unit. If they differ by a unit, by multiplication. So those are associated elements. Right, for example, 3 and -3 are associated in Z, because like we said, the units in Z are 1 and -1. So 3 and -3 are associates, just like 10 and -10 will be associates, and so on. As long as they differ by a negative, then, by a unit. In this case, the units are 1 and -1. So one could also say 3 and 3 are associates, in other words. Great. Now for us in factorization theory, we consider some elements to be the same. So 2 factorizations of the same element are called essentially the same. So these 2 factorizations are called essentially the same if they contain the same number of irreducibles. In other words, n is equal to m. And after a suitable reindexing, aj is associated to bj the other side. So that's what we call essentially the same. Otherwise, we call them essentially different. Great. So we're going to look at some examples of this. In this particular ring, Z with root -5 adjoined. So we have 6 is 2 times 3, but another person can say it's also -2 times -3, which is right. But for us, they are essentially the same. They first of all contain the same number of irreducibles, and 2 and -2 are associates or associated. Likewise, 3 and -3 are associated. On the other hand, 2 times 3 and these particular factorizations are essentially different. So for these, we call them essentially different. And we can have more, that in this particular ring, we have 81 giving us 4 copies of 3, but another person can say, yes, it's also negative 3 times 3 times negative 3 times 3. Another person can say, if when all of them are negative, still we get 81. For us, they are essentially the same because 3 and negative 3 are associates. Great. Whereas 81 having this factorization and that factorization, these two are essentially different factorizations. So this is essentially different from this. For starters, the lengths are different. Before we even look at the terms, the lengths are different. We already conclude these are essentially different factorizations of 81. Now, since we can have essentially different factorizations, moreover, they can be of different lengths. This has length for the number of irreducible factors, and this has length too. So since this can happen, we have a notion of set of lengths. So what is the set of lengths? We normally denote it by LR, or the set of lengths of an element R, and it literally consists of lengths of factorizations of the element R. So it's n in n such that R has a factorization of length n. So that is the set of lengths. For example, in this ring where we had 81 having these two essentially different factorizations, this is of length 2 and that is of length 4. No, this is of length 4, this is of length 2. So the set of lengths of 81 will be 2, 4. In particular, 4, 2, but yeah, it's a set, so we can always reshuffle. So this will be the set of lengths for that element, 81. So whereas for this particular element in int C, where we had 2 irreducibles and 2 irreducibles, so we had these two are essentially different, but they are of the same length. So our set of lengths will be 2, 2, but for us set of lengths, we don't allow multiplicities. So the set of lengths of this particular element will be just 2. Yes. So that's the notion of set of lengths, and it's the main theme for this talk. And now the set of lengths, these are the most studied invariants or objects in factorization theory, because they clearly describe the factorization behavior of that algebraic structure under consideration. So why do we care about the factorization behavior? We can deduce some other properties, maybe algebraic, arithmetic properties from the behavior of the algebraic structure under the factorizations. In other words, we study the factorization behavior and it tells us more about other properties, other algebraic properties of that particular algebraic structure. For example, if I had int z, like I don't know the prime ideal structure maybe of int z, but then I come across such an element which has 2 factorizations, or it has non-unit factorizations. I already conclude that int z cannot be a principal ideal domain. Because remember, so there is a connection. Every principal ideal domain must be a unique factorization domain. So the mere fact that this has non-unique factorizations, it already tells us in int z, you don't expect int z to be a principal ideal domain. So given an algebraic structure, even if I've not studied its ideal structure and I have information on its factorization behavior, I make deductions and conclude about its algebraic properties or the ideal structure or the arithmetic properties. Great. So sets of lengths, like I said, it's the most studied invariant in factorization theory. And Professor Frisch studied sets of lengths in int D, in int C in particular. In int C, we have her main result as this result. that for natural numbers m1, m2, mn, as long as they are greater than 1, there exists a polynomial h in int c with exactly n essentially different factorizations of those lengths. So that's what she did. That was her main result in that paper. What does that theorem say? That I have my finite set. I only need the numbers to be greater than 1. And I can choose any numbers I want. As long as they are greater than 1, I can allow multiplicities. Then I can construct a polynomial in int c such that that polynomial factors into 2 irreducibles, 4 irreducibles, other 5 irreducibles, other 5 irreducibles, and 7 irreducibles, and only those factorizations. And these are essentially different. That is what this result says, that we can do that in int z. Now, because for us, we don't allow multiplicities in sets of lengths, what does it mean? It already follows that every finite subset of natural numbers greater than 1 is a set of lengths of an element of int c. So any finite subset we pick, as long as the numbers are greater than 1, it's a set of lengths of an element of int c. Right, so this is a celebrated result in factorization theory. So today, the domains D, which have this behavior, are said to have full system of sets of lengths. In particular, a domain D is said to have full system of sets of lengths if every finite subset of natural numbers greater than 1 is a set of lengths of an element of D. So those are the domains with full system of sets of lengths. They satisfy this property. So when int z joined this group of domains with full system of sets of lengths, so it was expected that there are other domains D such that int d also has full system of sets of lengths. So the question was, are there other domains D such that int d has full system of sets of lengths? And we got a positive answer. That if D is a Dedekind domain such that D has infinitely many maximal ideals and these are of finite index, then int D has full system of sets of lengths. So we got these Dedekind domains. They must have infinitely many maximal ideals and those maximal ideals must be of finite index. Then we have int D having full system of sets of lengths. In particular, we proved again that for natural numbers m1 up to mn, as long as they are greater than 1, there exists a polynomial h in int d with exactly n essentially different factorizations of those lengths. So that's what we proved again in this general case. These Dedekind domains, so just like in Z, where we have unique factorization of elements into prime numbers, in other words, unique factorization of integers into prime numbers, we have unique factorizations of ideals into prime ideals in Dedekind domains. So they have that similar property, but in the case of Dedekind domains, it's general in the ideal setting. Yet for the integers, we are specifically under elements. So we have unique factorizations under elements. Great. So these Dedekind domains are our usual domains actually. Integers themselves belong to those Dedekind domains. And more generally, rings of integers of number fields are also part of those Dedekind domains. So for example, the examples I gave at the beginning, Z with root -5 adjoint, Z with root -14 adjoint, all those are among those Dedekind domains. Great. Now, similar results have been obtained using transfer mechanisms. So what are these transfer mechanisms? So several monoids with full system of lengths have been obtained using transfer mechanisms. The first of its kind was by Professor Kainrath in 1999. So what are these transfer mechanisms? The tool there is what we call a transfer homomorphism. So the transfer homomorphism transfers factorization properties from one monoid to another. In particular, if theta from a monoid H to M is a transfer homomorphism, then U in H is irreducible in H if and only if its image is irreducible the other side in M. So in other words, transfer homomorphisms preserve irreducibility. Similarly, the set of lengths of an element U in H is exactly the set of lengths of the image of U, this other side in M. So those are transfer homomorphisms. And now, under transfer mechanisms, in case I want to study factorization properties of my monoid H, what I can do is to get a friendly monoid, maybe where that property that I need is already known. Then I construct a transfer homomorphism from my monoid of interest to the other monoid, which is already known, and then pull back what is known here and get it for my monoid H. So those are the transfer mechanisms. And it's a very important tool in the monoid setting, actually. Okay. Some monoids that have been used widely in these transfer mechanisms are what we call the block monoids, or monoids of zero-sum sequences. That these have been widely investigated, that if I have my monoid H and I want a specific property, since it's already known here, I can construct a transfer homomorphism to a suitable block monoid and pull back what is there and use it for my monoid of interest. So a property the block monoids have is that if U, V are irreducible elements of a block monoid with U fixed, then the max or the longest factorization of UV, of the product UV, is bounded by some constant that depends on what is fixed. If I have UV are irreducible elements of a block monoid, then this, because this is maximum, it's the length of the longest factorization. So this is noting the set of lengths. So we are looking for the longest factorization, and we are considering its length. That length must be bounded by some constant that depends only on what is fixed. And now, since transfer homomorphisms preserve sets of lengths and they preserve also irreducibility, it follows that any monoid which allows a transfer homomorphism to a block monoid must have this property, because the set of lengths of that monoid, of that particular element in a monoid, must be exactly the set of length of its image, the other side in the block monoid. So if this is satisfied in the block monoid, then the original elements must also have that property. So block monoids have been used widely, like I said, that actually today, monoids which allow transfer homomorphisms to block monoids, block monoids are called transfer cruel monoids. So like I said, another name for block monoids, these are monoids of zero-sum sequences. That's a more common term, maybe. So monoids which allow transfer homomorphisms to block monoids are called transfer cruel monoids, because in particular, a block monoid is cruel, and if I can have a transfer homomorphism to a block, I can have a transfer homomorphism from a block monoid to any cruel monoid. Great. So for int Z, we showed that this is not possible. In other words, Professor Frisch, in her original paper, showed that this can be violated in int C, meaning we can't have a transfer homomorphism to a block monoid. Why? Because in int C, this does not hold, Yet, any monoid which allows a transfer homomorphism to a block monoid must have this property. In particular, she showed that for every n natural numbers greater than 1, greater than or equal to 1, there exist irreducible elements, HGIs, in INC such that when we fix x, XHX factors into the GIs. In other words, we are fixing x and the product is factoring arbitrarily. This is true for any n. So it's not bounded in particular. So those are that's the property that violated the other property in block monoids. What does it mean? This property means that actually the multiplicative monoid of int C, in other words, the non-zero elements of int C under multiplication, is not a transfer monoid, because this property, the property for block monoids, this property where the length of the longest factorization is bounded by something that depends on what is fixed, is violated in int C. So the multiplicative monoid of int C is not a transfer monoid. We also showed the same actually, that for Dedekind domains with infinite many maximal ideals, all of finite index, we can construct H and the GIs in int this such that when we fix X, the product XHX factors arbitrarily. What does that mean? It also means that the multiplicative monoid of int D for this particular Dedekind domains is not a transfer monoid. So these results not only rule out transfer mechanisms in this structure of integer valid polynomials, but also gives these counter examples of monoids which are not transfer monoids. Yes, so those are the transfer mechanisms. And then I would like to share with you the tools, illustrate the tools that we use in the main result. Remember the main result? We had that we can indeed construct a polynomial that factors into those given, which has length of that given set. It has factorizations of length of that given set. So that's what I want us to look at next. In particular, we want to construct a polynomial H in int C that has its set of lengths as 2 and 3. So it factors into 2 irreducibles and also has a factorization of length 3, or factors into 2, 3 irreducible. And so that will bring out the tools that we use. So what do we do? So we start with 2 numbers that depend on this, 1 less than this, on what we want. Yeah? So this n1, n2 is now 1, 2. This 1, 2 is not this 1, 2, but it's 1 less than 2 and 3 less than, and 1 less than 3. So that's the 1, 2. So we start with such as, say, we want 2, 3 at the end, we start with one value less, yeah? So we have 1, 2. And then we construct or we calculate a number that depends on these ni's. What's that number? It's the square of the summation of the ni's minus the sum of the squares. So this is a very specific choice because we'll see at the end that what we want, we shall arrange n elements in a square matrix of size this. And we leave out the block diagonals. That's why I'm having a minus here. I will illustrate later. So this is a careful choice of n. Great. So our n in this case is 4. So we have this sum, which is a 9, and then we subtract off the 3. The 5, sorry. We subtract off the square, the sum of the squares, which is a 5. Great. So n is 4. Next, we pick a prime number p which is greater than n. For instance, we picked 5. Another person can pick 7. As long as the prime is greater than 4, you're good to go. And then we construct, but I chose 5 because, as we shall see later on, computational things come in. So we construct a complete system of residues mod P that does not contain a complete system of residues mod any prime less than P. What do I mean? We can pick such as C. The primes less than P, we have 2 and 3. We don't want a complete system of residues here. Whereas we want a complete system of residues mod 5. In other words, we want every element of, the residue classes of C mod 5C to be represented. And indeed, this is representing the 0 residue class. This is representing 1. This is representing 2. This is representing 4. And then this is representing 5. And we don't have a complete system of residues mod 2 because otherwise we would have even numbers here. We don't have a complete system of residues mod 3 because the 0 residue class of 3 mod 3, the 0 residue class of C mod 3Z is not represented here. In other words, we would have a multiple of 3 here. So this is our set. We've picked a complete system of residues mod 5. What do? We partition this set into 2 sets such that one of the sets has exactly our 4 elements. And say we've picked 5, 1, 7, 13. So the order really doesn't matter. One can pick 1, 7, 13, 19. As long as we pick 4 elements, we are good to go. And then we set Sx to be now the product of the x minus, or the remainders. For our case, we only left out 19. So this will be just x minus 19. If we had picked P to be, let's say, 7, we would have more values here. In other words, we would have more redundancies. So we would have x minus 19 and other values. Because for this particular we want exactly 4 of them. Great. So in other words, we would have more 2 values to have 7 values. Great. So what next? So we arrange these elements into an array. That, like I said, it's the reason for this. So we arrange this in an array, something like this. It is this by the size is that, yeah, summation of the ni's. Our ni's, we had 1 and 2, so the summation is 3. We have a 3 by 3 matrix. So we have a 3 by 3 matrix, and we've arranged our elements there, really arbitrarily. We can put 1 anywhere as long as our elements are all there. And like we said, the minus the other side on n was because of this one, the block diagonals to be empty. So those are our elements. And then we construct polynomials from this array. How? What you see as F1, 1 up. So this means I'm considering the first block of rows and first block of columns. And then this one, in this case, in any case, we have just 1 row and 1 column. So this is first row, first column in the first block of rows and first block of columns. So that's why we have the first block of rows, we have this. That's why we have a 7, x minus 7 and x minus 13. And then the first block of columns, first column is this. We just have just 1 of it. So x minus 5 and x minus 1. So for that particular block, we have just 1 polynomial because n1 was 1. Then we go to the second one. This means in the second block of rows, consider the first row and the first column. So we have this, and this is the second block of rows and respectively second block of columns. We have the first row and the first column. That's why we're having x minus 5 and x minus 7. Then this says second In the second block, consider second row and second column. So this is x minus 1 and then x minus 13. So these are our polynomials that we generate from such an array. If we had n, for example, if n was bigger, so we'd have maybe a 4 by 4 matrix. Yeah. Great. At this point, we are almost there. So what do? Our preliminary polynomial is hx, where we have the numerator, we recall the little s and then the fi's. So there is math behind, because an element, a polynomial of this form is integer valued if and only if the root of the numerator contains a complete system of residues mod that prime p in the denominator. So when you go back a little, when you look at these values, we have just part of the complete system of residues, mod 5. But when we bring back, so we have 1, 5, 7, 13, but remember there is one thing we kept, which we now brought in as Sx. So now this is integer valued because we have a complete system of residues. When Sx joins these ones, we have a complete system of residues because as we see, these elements are actually repeating. So we are always complete, really. Great. But now because these are floating around, these are not irreducible, in our construction, we glue them. So we replace each of these fi's with corresponding monic irreducibles, capital Fi, without losing the information regarding this fixed, we call it a fixed divisor. In particular, what was F1, 1, this polynomial is not irreducible. We have what we call a gluing lemma that ensures that we can get a polynomial that is irreducible, but without losing the properties that this other one was contributing. So such a polynomial is this. I calculated it. So like we said, the proof is constructive. One can explicitly calculate something. So this is the corresponding, this is irreducible. So in the irreducibility, we are using Eisenstein irreducibility criterion. In other words, if I have such an element in Zx, all I need is, if I can find a prime number, let's say because we are in Zx in any case, such that that does not, n is not divisible by that thing. For example, 2 in this case is the right choice. All these coefficients must be divisible by that prime number. And then the last value, n naught, must not be divisible by p squared, in this case 4. So that's the Eisenstein irreducibility criterion. So in this case, we also have, for this particular one, we get a corresponding irreducible one. Still we check irreducibility by Eisenstein irreducibility criterion. So that is ensured in our gluing lemma. Likewise, 2 does the job here. Likewise, even here, 2 does the job, the prime 2. Great. So now these are our capital Fi's. Now our required polynomial is when we've replaced these little Fi's that were floating around with these solid ones that are irreducible. In particular, Hx, or the required polynomial, will be Sx, the capital Fi's over P. That will be our polynomial. How does it factor into what we needed? This is how it factors. For each block, for example, block 2, we cover, together with the Sx, we have the root of this numerator the roots of that numerator is a complete system of residues mod P, which in any case, our P was 5. And then this is not necessary. Then likewise, for this particular block, we are covered, then that won't be necessary. So to take you back a little, before here. So we see that for this particular block, all the elements in here are covered. And for this particular block too, I need both of them to cover all these elements. So that is what is happening. That once I have F1, I don't need these two. And if I have these two, I don't need this one. And if I have one of these and maybe this other one, there will be a redundancy. That's what is happening. Great. So that's what's happening. That what we need is a specific block, then we can drop off the other one. What we need, for example, here it's F1, then these are no longer necessary because the roots of this on its own, remember in the construction of the irreducible, we made sure that we don't lose any property as we are moving from those which are not irreducible to the irreducible one. So this behaves exactly the same way as the other products of the monics. And this will be our polynomial factoring into two irreducibles and into three irreducibles. So that's how we construct these polynomials. So I chose 2, 3, but one can also choose 2, 3, 5, but of course, more work is needed in that case. I mean, the computations. But this is the idea of the tools in general. So this was in particular for Z. So what we did in the Dedekind domain case, we moved really from elements to ideals completely. We moved from elements to ideals. So the construction was in form of ideals in particular. Great. So these are some of our references. This is the general reference for integer valued polynomials. I learned from Professor Frisch the other time that Professor Schaberth is actually working on a new version of this integer valued polynomial. And then here is a friendly introduction to integer valued polynomials, what you should know about integer valued polynomials. The general reference for non-unique factorizations is this one. This one. And then here you can find Professor Keinrath's result for these monoids with full system of sets of lengths. In other words, transfer mechanism, where transfer mechanisms were used. In the number 5 is where you can find Professor Frisch's construction for prescribed sets of lengths of these integer valued polynomials. Like we said, when we don't put G, we are referring to int C. And then this is the general reference for this talk, where we studied sets of lengths or factorizations of integer valued polynomials on those Dedekind domains. And number 7 is a survey, actually, on sets of lengths. Most of the things, recent results on sets of lengths can be got there. And number 8 is the most recent one on sets of lengths. To the best of my knowledge, this is the most recent result on sets of lengths. That is what I had to share with you. Thank you.